Hello from Scranton, Pennsylvania. Not sure how I ended up here, um, but hey, it's a cool place to be. Anyways, welcome to week 6 of our remote learning. Week 6 of 8. Now, if you have been reading your emails, hopefully you've seen that we're going to actually end the year a little early this year. So instead of going all the way to May 22nd, we're going to end just a bit early, so it gives us a little bit of time, as teachers especially, to wrap things up and make sure everybody's on the right track. So that being said, we were planning on ending early anyways. So we are going to reserve that last week for catch up, and if you needed to make up any work, then that was going to be that last week. So it's falling right into our plan. We're not really doing anything different. Okay, so that means we've got 2 weeks left. We got this week and next week finishing up our three-dimensional modeling unit here. Okay, so hopefully you're on the right track. Hopefully you've been keeping up, watching those other videos, and you're ready to move on. But before we get there, again, like every other week, we got some riddles here. Okay, so first one, nice history lesson. With the conclusion of the Turin Games in 2006, there have been 20 Olympic Winter Games. However, there have been 21 gold medals awarded in men's ice hockey. How can this be? Obviously, hockey, it's not a game where you end up tying, maybe, I don't know. But answers in 3, 2, 1. Hockey was actually played once in the Summer Games. Ha! Who would have thought? Yeah, anyways, just Olympics because it was supposed to be an Olympic year, but that's getting moved to next year. All right, next one. You can walk across a bridge and you see a boat full of people, yet there isn't a single person on board. How is that possible? Not a single person on board, but it's full of people. Did you guess it? They're all married because they're not single. Yeah. All right, last one. This one's up for debate. If it takes 6 men 1 hour to dig 6 holes, how long does it take 1 man to dig half a hole? Answer in 3, 2, 1. Apparently, you can't dig half a hole. It's already a hole, no matter what. Or is it? Can you dig half a hole? How many holes does a straw have? Do you say 2? Do you say 1? I say infinite, but hey, that's up for debate. Anyways, can you have half a straw? If it's half a straw, isn't it? I don't know. Mind blown. Just like I don't know where I'm disappearing to. Anyways, okay. So we're in our 3D unit. So let's go ahead and continue with that. So let's pull those up here. And let's go ahead and get started here. Okay, so week 6, three-dimensional modeling, what we're taking a look at here. Okay. So our goals for this week: identify the shapes of cross sections formed by cuts to a solid. Okay, keyword there is our cross sections. Okay, second part: determine the volume of prisms, and then determine the volume of pyramids. So we've talked about prisms and pyramids. Last week we talked about the surface area. Now we are looking at the volume. Okay, you've probably heard of volume, and we'll get to there in a second. All right, so first goal here, talking about cross sections. Okay, so what is a cross section? It's the intersection of a solid figure and a plane. Okay, so if I were to take a plane and slice off part of a figure, what am I looking at? Now, a cross section, it's always going to be two-dimensional. Okay, so it's the 2D picture of a 3D shape. Okay. Last week we talked about surface area, so I thought, hey, let's talk about another two-dimensional kind of characteristic of our three-dimensional figure. Okay, so if you take a look at this loaf of bread, if I take that solid figure, it's a three-dimensional loaf of bread, I cut it down, okay, it's saying, what surface are we looking at? Well, in this case, we're looking at this slice of bread. Okay, now, in our figures, right, this is we could call this a rectangular, it's probably a square pyramid. But we want to know, okay, if I take this plane, right, I take this really sharp knife and I cut along this plane and I look at it from that angle, what shape, what two-dimensional shape am I looking at? Okay, well, if you think about this in this first picture, okay, if I cut parallel to that base and I look down on top of that, well, then I'm probably going to end up looking at a square, if this is indeed a square pyramid. Okay. If you think about in the second shape, if I cut diagonally, okay, what shape are we going to be looking at? Well, if it's a square pyramid, well, the further you go down, remember down here, okay, let's change colors. Let's use a red. That's going to be longer because it's a wider base than it is up here. So if you think about that, longer base on bottom, shorter on top, connect those, it's going to be a trapezoid. Okay, and then the last one, if I cut straight down from the top, okay, perpendicular to that base, well, it's obviously coming to a point up here, and then it's a wide base, so that's going to be a triangle. So with the cross sections, the biggest thing here is just being able to visualize what you're cutting. I think that's the hardest part about these, and for those of us that are a little spatially challenged, okay, it's a little harder to visualize that. So just looking at these and practicing and seeing different examples, I think that's going to help us out. Okay, now, why do we talk about cross sections? Well, if you go into any sort of engineering, manufacturing, anything like that, you're going to see a lot of cross sections, right? We live in a 3D world, but in order to put this onto paper, right, we need a two-dimensional kind of drawing. So if you look at this first shape here, right, that's our what we call our orthogonal view of a 3D view, but I'm going to look at it from each side. So if I look at the back view, the left side view, the top view, those are all cross sections, if you will, of just a two-dimensional drawing. Okay, same thing here. You could take an even more complicated picture, right, 3D picture, and then make your different views. And those are more or less your cross sections. Okay. Now, where are we going with these cross sections? Well, if you think cross sections, okay, they're going to be slices of your three-dimensional figure. Well, if then you put your cross sections back together, you create that three-dimensional object. So if I like to think pieces of paper, right? We think pieces of paper, they're more two-dimensional. They don't really have a width. Yes, are they technically three-dimensional? Of course, but we look at them as a two-dimensional object. But if you put 500 pieces of paper together, you end up with a ream of paper. It's now three-dimensional. It has depth. So where this, knowing these cross sections is going to take us is into volume. So where we're going to use this is, how do I calculate volume of these figures? Well, to first do that, I need to know what is volume. Okay. Now, to do that, we're actually going to jump over to my friend who's going to explain that. So take a look at this video, and hopefully I like the visuals in it, so hopefully it helps out.
In this lesson, we're going to learn about another important geometry quantity called volume. Specifically, we're going to learn what volume is, and what kind of units we use to measure volume, and how we can calculate the volumes of a few simple geometric shapes. The first thing you need to know is that volume is a quantity that all three-dimensional objects have. But to understand what it means, it will help if we back up just a little and start out with a one-dimensional object, like this line segment. To measure a one-dimensional object, we need a one-dimensional quantity, which we usually call length. The length of this line happens to be exactly 1 centimeter, which is a common unit for measuring length. And in the Math Antics video about area, we saw that if we move or extend this one-dimensional line in a direction perpendicular to it by a distance of 1 centimeter, it forms a two-dimensional object called a square. Two-dimensional objects are measured by the two-dimensional quantity that we call area. Because the original line was 1 centimeter long, and we extended it a distance of 1 centimeter, the amount of area that this square occupies is 1 square centimeter, which is a common unit for measuring area. Okay, now imagine that we take that two-dimensional square and move or extend it in a direction perpendicular to its surface by a distance of 1 centimeter. It forms a three-dimensional object that's called a cube. And to measure a three-dimensional object like this, we use a three-dimensional quantity called volume. Volume tells us how much three-dimensional space, or 3D space, an object occupies. Alright, but how much volume does this cube have? Well, since it was made by extending 1 square centimeter a distance of 1 centimeter in the third dimension, we say that its volume is exactly 1 cubic centimeter, which is a common unit for measuring volume. So square units are used to measure area, and cubic units are used to measure volume. Since square units are made by multiplying two one-dimensional units together, like centimeter times centimeter, we can abbreviate them using the exponent notation, centimeters to the second power, or centimeters squared. And since cubic units are made by multiplying three one-dimensional units together, like centimeter times centimeter times centimeter, we can abbreviate them using exponent notation, centimeters to the third power, or centimeters cubed. And just like there were different sizes of square units, like square inches, square meters, or square miles, there's also different sized cubic units, like cubic inches, cubic meters, or cubic miles. See how area and square units are related to volume and cubic units? And there's another similarity too. Do you remember how you can use square units to measure the area of any 2D shape, not just squares? Well, you can use cubic units to measure the volume of any 3D shape, not just cubes. To see how that works, take a look at this 2D circle and this 3D object called a sphere, which is like a ball. Just like you can use a bunch of small squares to approximate the area of the circle, you can use a bunch of small cubes to approximate the volume of the sphere. And here's the really cool part. The smaller the squares you use, the closer their combined area will match the area of the circle. And the smaller the cubes you use, the closer their combined volume will match the volume of the sphere. Alright, so now that you understand what volume is, and you won't confuse it with surface area, we're going to spend the rest of the video learning how to calculate the volumes of some basic geometric shapes. But before we do that, I want to quickly mention something important about terminology, or the words we use to describe things in math. Most of the time, people agree on what to call things in math, but not always. And that's especially true when it comes to the words that we use to describe the dimensions of geometric objects. Take the words length, width, and height, for example. If I have a rectangle, I could name its two dimensions length and width, like we did in the area video. But I could also name them width and height if I wanted to. The actual names of the dimensions really aren't important, so different teachers might use different names. The important thing is to be flexible and realize that the math concepts are the same, even if different words are used to explain them. For example, the area of a rectangle is always found by multiplying its two side dimensions together, no matter what they're called.
Alright, and thank you to Math Antics for that video. Again, I like the visuals and the way that he explains things. So, anyways, decided to jump on a plane, leave Scranton, and we'll see where I end up. But let's go ahead, let's recap what he was talking about in that video. Okay, so volume, recall that it's the measure of the amount of space that the solid encloses. Okay, so if you think about a box, it's how much space is in that box, how much space something takes up. Okay, now in that video, he talked about a cube. Right, so if you take a square and you extend it 1 unit, then you end up with a cube with sides of 1, 1, and 1. Right, well, when I think cube, I think Rubik's Cube. So let's take a look at this Rubik's Cube here. Right, so if I just take a look at this corner cube, this has dimensions of a 1 and 1, so it's a 1 unit, or 1 square unit in the front here. Okay, and then we extend it 1 unit into the Rubik's Cube. So this whole block here has a volume of 1 cubic unit. Well, so then you need to think about how many blocks are there. Well, on the front face, right, I have 3 units across, I have 3 units up, so that gives you 9 square units, right? So 3 times 3 gives you 9, but then you also extend this 3 units back, right? Because you have 3 of those blue units, 3 of those red units, so then you multiply that by 3, which gives us 3 cubed, or 27. And when, again, just like he said in that video, we have units cubed. Okay, so for volume, our units will always be cubed. Centimeters cubed, inches cubed, yards cubed, no matter what, something cubed. Okay, let's take a look at another example here. All right, so if I look at just the front face of this rectangular prism, right, you can see, well, I've got 2 units high and 1, 2, 3, 4, 5, 6 units across. So there on this face here, right, you have 12 units squared. All right, well, you're taking those 12, and how many layers do you have? Right, you have uh, 1 layer, so that would be the 12. You have 2, 3, and then 4. So you would take this, you would multiply by the 4, right? 4 units back. So that's where you see we have 3 sets of units there, so that would give us 48 units cubed. Okay? So that's just simple examples of our volume. Okay. Now, if we are ready and we understand what volume is, we understand what those cross sections are, then I will show you in the next video how to calculate the volumes of the rest of our prisms and then our pyramids. Okay. So if you feel comfortable, hop on to the next video and we will see you over there.